All right, let's imagine that we've got a beam of light passing through a square block of material. So we have a square block of material, and let's say the side length is going to be 7.75 centimeters. And we have a beam of light hitting it at an angle of 40 degrees with respect to one surface. Now, let's say that the outside is air, so the index refraction is approximately 1, and then inside the index refraction is going to be 1.56. All right, so what's going to happen? Well, if the block were not there, then the beam of light would have just kept going straight like that. Okay, but the block is there. And so what's going to happen is instead it's going to refract and go to this surface over here. So it's going to now refract, and we're going to have another angle theta 2. Okay, so we know that N1, if we call this N1 and then that N2, and that's theta 1. So N1 sine theta 1 equals N2 sine theta 2. So that means that this is just sine 40 degrees equals 1.56 sine theta 2. So we could then say that we can solve for theta 2. So theta 2 is going to be the inverse sine of sine 40 degrees divided by 1.56. So theta 2 comes out to be 24.3 degrees. All right, so our block right here, square block, we have something coming in here and it refracts. So theta 1 is 40 degrees. That's theta 2. We just derived that theta 2 is going to be 24.3 degrees. Okay, now what's going to happen at this other surface? Well, from using geometry, we know this is a square block, so these are all right angles right there. Okay, so that means that this angle right here, that means this far side and the near side are parallel, so that angle has to equal this angle. Okay, so now it's going to refract again right here. Okay, so that angle up here, so the question angle right here, so the unknown angle, well, we know that N2 sine theta 2 equals N1 sine the question angle. Well, wait a minute, this is 1.52 sine of 24.3 degrees equals 1 times sine of theta question. You do some math, theta question is 40 degrees. Well, it's got to be 40 degrees. So this has got to be 40 degrees up here. How do we know that's got to be 40 degrees? Well, because this looks exactly like that. So by symmetry, we didn't even have to do any math right here. We could have just looked at it and said, well, the two places I circled are mirror images of each other. They've got to be the same. It doesn't really matter whether light's going this way or light's going that way. It's doing the exact same path. And so we would say, therefore, that it's got to be a mirror image. So we know that's got to be 40 degrees. Well, so we got our square. If light had gone straight through, it would have done that. But it did not. Instead, it deflected to there and went like that. Okay. So, and then off in that direction. So that's going to be 40 degrees, just as this was 40 degrees. And theta 2 and theta 2, so theta 2 was 24.3 degrees. Now, by doing a little bit more here, we can say, well, okay, that's going to be 40 degrees right there. And so that means that these two lines are parallel with each other. Well, if they're parallel, what that means is that the light was deflected some distance d right there. And instead of going straight through, it followed a different path and is now going parallel, but shifted over some distance d. So I want to know, what is this deflection distance right there? Okay, so how do we find that deflection distance? Well, we look at it and say, well, we need to actually do some more math up here. And so what I want to do is, again, redraw this. So it goes off that way versus going straight. Okay, so draw a perpendicular right here. I'm going to call that distance x1 and call that distance x2. The difference in x1 and x2, that's going to be delta x. Okay, now we already know that this is some y distance, which I already told you at the very beginning was 7.75 centimeters. Now, this angle, theta 2, this full angle is theta 1. Well, if we look at this, then x1 over y is going to be the tangent of theta 2. So that means x1 is going to be equal to y tan theta 2. Okay, so that is going to be equal to the 7.75 centimeters tangent of 24.3 degrees. So x1 comes out to be 3.50 centimeters. Well, what about x2? Well, you look at that and you find that x2 over y equals tangent of theta 1. So that means that x2 is going to be y tangent theta 1. So that's going to be 7.75 centimeters times tangent of 40 degrees. So x2 comes out to be equal to it turns out to be 6.5 centimeters. So delta x, that's going to be x2 minus x1, so that's going to be 3 centimeters. Okay, now how does that? So the beam, if it comes straight through, but it didn't, it went there and there. So if I draw a perpendicular right here, I know that this angle is 40 degrees. That's 90 degrees, so this angle is 50 degrees. This is my deflection D, there's my delta x. So if I look at it, then I see that D divided by delta x is going to be the sine of 50 degrees. So D is delta x sine 50 degrees. So D is 3 centimeters sine 50 degrees. So the deflection comes out to be equal to 2.30 centimeters. Okay, and so that's how we do this problem. And so we just found the deflection, and obviously this would be different if it were underwater, because the external angle would be different, or rather the external index refraction would be different, and so that would change the angle of deflection, or the angle of refraction, than the angle of deflection, I mean the deflection distance. It would also be different if the incoming angle were a different angle. If the incoming angle were not 40 degrees, then this other angle would be different, and so that would have changed the things on the far side as well. Now, notice what I've done with this problem is I had to redraw it multiple times, labeling things, because everything was all the same color with what I'm using here at home, then I had to redraw it. If I were doing this myself on a piece of paper, I would use some colored pencils, and I would have drawn this and labeled every part of it in different colors to try to keep it all straight. And so that's a strategy that with geometric optics, I strongly encourage you to do, is draw it in different colors and to draw it big. The bigger you draw it, the smaller the little angles you can put on there and label things. And that really does help. But I would do it big and in different colors, trying to make it easy to see all the parts.